You can see this? Everything's coming up right? Okay, good. 15.1 is endothermic and exothermic processes. Okay. Endo, when you see the term endo, what does that mean? It's going into something, and exo means that it's coming out. Kind of like we have an endoskeleton and bugs have an exoskeleton, right? They're skeletons on the outside. So there's different ways that people use those prefixes. Thermic means heat. So when you see therm, that means heat, like a thermometer. Okay? So you can kind of break those words down and get stuff from context. One of the things that we need to talk about in terms of heat is that heat is either going to be released or it's going to be absorbed. Okay? And we need to talk about the fact that only heat moves. Cold does not move. So if you take your hand and you put it down on the desktop and it feels cold to you, that is not the cold coming into your hand. It's actually the heat coming out of your hand into the desk. Okay? And eventually, if you leave it there long enough, they'll equalize. Okay? Certain things change temperature more quickly than others, and that has to do with something called specific heat, which we're going to get into in the coming days. You need to talk about also the difference between the system and the surroundings. So the system is what you're studying. So it might be whatever's inside the beaker, whatever's inside whatever's going on, okay? And then the surroundings are what's outside. So like I said, if you put your if you have I did that experiment with the alcohol and the water, and I brought it around and I made you feel it. Do you remember that? Okay. How did it feel? Warmer, right? That was because heat was coming off of that and going into your hand. Okay. And it was coming out of the system, the alcohol and water, and going out into the surroundings, which happened to be the glass in your hand that you were touching. Okay. This should be heat transferred, not heart transferred. Let's get the R out of there. It'll let me. Nope, it's not going to let me. So enthalpy is about the amount of heat transferred, not heart. Sorry about that. Let's get rid of the R there. There we go. So there are no hearts involved here. Sorry. Trying to get my eraser to show up, but it's not showing up here. There it goes. I just had to touch on something here to make it happen. Okay, so it's important to always define what the system and surroundings are when you're looking at a problem. Heat is going to be documented with the letter Q in our formulas. I don't think we do a formula at all today. No, we'll get to formulas the next couple days. Today you're not having to deal with them yet. When you're looking at heat getting transferred, that heat is coming from the system and then it's going to the surroundings. So this would have been an example of that alcohol where you had the energy of the system, which was the alcohol and water mixing together, and then you had energy of the surroundings, which it was going into. Okay. If no work is done, the heat lost is equal to the heat gained. So you have this for your system. Quantity of the amount of heat is the amount of thermal energy transferred from something that's hotter to something that is colder. Okay. So when your mom yells at you in the winter, shut the door, you're letting the cold in, you can tell her, cold doesn't move, Mom, only heat does. And then you'll get backhanded. At least you will. And so the proper way to phrase that is you're letting the heat out in the winter. Okay? Make sense? All right. I'm not funny, am I? I'm sorry. All right. If thermal energy is transferred from the system to the surroundings, the heat is negative. If the thermal energy is released or is transferred from the surroundings into the system, then it's going to be positive. Okay, so this will feel hotter. If you touch it with your hand, this will feel cooler. So in this process here, those cold packs that are in first aid kits, have you seen those where you break a seal? What you're doing when you like twist that and break that seal inside is you're actually mixing two chemicals together, and it's an endothermic reaction. So it's bringing heat in from the outside and storing it in the bonds of those chemicals inside there. And because it's pulling heat in, it's going to feel colder on the outside. So that's how those cold packs work. Likewise, you may have in the winter those things that you put in your pockets that keep your hands warm, like if you're going hiking or something like that. That's how those things work, except just the opposite of these. Another example of this, where instead of thermal energy, which we're talking about thermal, but it's just another example of where you would see this, would be those glow sticks where you break the seal, and instead of it coming out as heat, it's actually coming out as light that it's emitting. But I digress. All right, so work then is the energy needed to move something against a force. We usually think of that in terms of expanding gases, like if you're pushing on a piston, for example, in a car. So when you burn fuel in the car, that heat is transferred to the system of the vehicle, and it's generating heat, and that's what's pushing up on the pistons in the car and making them move up and down. Okay? I can't get any more complex with vehicles than that. That's about as much as you're going to get out of me. But that's kind of the idea. Now, you may know more about it because you probably had some auto stuff already, Noah. But anyway, you got these pistons are moving up and down. They move up and down because the gases are expanding. Okay. So if the system is pushing on the surroundings and expanding the piston, then the work is negative. If it is compressing, then it's going to be positive. All right. Endothermic reactions. You need to be able.
Interruption. Michelle Meyer, dial 5252. Michelle Meyer, dial 5252.
You need to be able to look at a graph and determine what's going on from that graph. Okay. So if you are dealing with endothermic processes, oops, that's not the right thing. I wanted this guy. If you're dealing with endothermic processes, you are going to have heat absorbed from the system. Your enthalpy value will be positive. The products will have higher energy than the reactants. Okay? When you're looking in terms of graphs, this is what that would look like. You're looking at energy on the side here, the potential energy. Your starting reactants are here. They need something called activation energy. So the activation energy is between here and here. That may be a match. It may be a spark. It may be the sunlight shining in on plants for photosynthesis. So that energy can come in a variety of different ways. And that activation energy needs to be met in order for these products to be produced. When the products are produced, then you're going to have a higher amount of heat than what you started with. Your delta H then will be a positive value. In terms of phase changes, so we've talked about phase changes this year. If you have to add energy in, then you're going to have phase changes that are endothermic. And we talked about these being endothermic when we discussed them back in chapter 12, I believe it was. Okay, so your phase changes, if you wanted ice to melt, you'd have to add energy in. That's why it's endothermic. So melting. boiling, vaporization, sublimation. All of those phase changes are going to be endothermic. Any changes that occur, why is that? Go away, go away, go away. Okay. Any changes that involve breaking or separating. So what do I mean by that? Let me see if I can find space to draw here. Up here. I'm going to just hijack some space up here. So if I have sodium chloride, for example, and I want to put that into water, a couple things have to happen. Okay. I've got my water molecules over here. Remember, those water molecules are attracted through intermolecular forces to one another. Okay. This is my negative end of my water. This is my positive. The positive end of this one's attracted to the negative end of that one. In order, when we put this into that water, in order for this to dissolve, this stuff has to separate. So you've got to get your sodium ions separated from your chlorine ions. That takes energy. To separate these things out, you've got to input some energy into that to make that happen. Okay. The other thing that has to happen is these water molecules have to separate from one another. They're attracted through LDF, through dipole-dipole, and hydrogen bonding. So those three things, that has to separate. They have to separate from one another. So when we're talking down here about breaking or separating, that's what we're discussing, okay? And if you think of these as kind of like magnets almost, if you tried to pull two magnets apart, you would have to actually put some energy in to make that happen, right? So when I'm thinking about these and trying to figure out if they're endothermic or exothermic and I'm pulling them apart, that's where my brain goes. I imagine trying to physically pull two magnets apart, and I'm like, I'd have to put some energy into it. Okay? Heating curves. When you're looking at something heating, okay, you're adding energy in at every one of these steps to get this stuff up to steam. Okay? If we flip to the other side then, and we're talking about exothermic processes, trying to change my color over so it looks a little different. So exothermic processes here, heat is going to be released. So this is going to feel warm. Your enthalpy change then is going to be negative. So when we're looking at this guy right here, this is going to be a negative value. So enthalpy is negative. The products are in lower energy than the reactants. So these products down here have a lower energy than these. We still will need some, what? What is this called right here? Activation energy. And I'm introducing that term right now because later this week or next week, I'm going to come back to that term. It comes back to us. Okay. All right. Keep going down here. Phase changes are going to be, oops, that's an eraser. That's a highlighter. That's what I want. Phase changes are going to be your freezing, your condensation, and your deposition. This is where it goes straight from a gas to a solid, like the frost on your windshield. If we're looking in terms of cooling curves, and you guys had to do these two curves back on one of your labs, if you remember correctly. These are your cooling curves. So we're losing heat here. A lot of times when you bring these substances together, you will end up with, it can go one way or the other. In terms of like when we're doing your with the alcohol and water. Okay, it was releasing energy. Okay, these can end up absorbing some more energy in the process, but it doesn't require energy. So when you're breaking these bonds, you're going to have to put energy in. When this stuff comes back together, and I have that drawn wrong. Yeah, I can do it like this though. When I have the oxygen end, and the oxygen end is going to point towards the sodium. Why? Yeah, the oxygen end is negative, so it's going to orient itself around the positive ions. This is going to release energy. Okay? And the hydrogen ends of this one are going to be around the chlorine. This is a question on your final, by the way, where you have to interpret one of these images. So when this happens, if this takes more energy than is released, then it's going to feel cold. If this releases more energy than it took to separate these things, then it's going to feel warm. So, like I said, when a solution forms, there's 3 overall processes that take place. The solvent has to overcome its intermolecular forces. So, in other words, the water has to break away from the other water molecules. The solute has to break away. So, they have to overcome their forces. These two are endothermic. They're going to require energy. It's like pulling the magnets apart. The solution and solvent recombine, that's exothermic. When you bring 2 magnets together, do you have to do anything to get them to stick? They just snap. Okay? So that's what energy, and you hear a clack sometimes, right? That's energy being released. You can hear that. Okay? If this process releases more energy than it took to overcome, then the overall delta H will be negative because it's releasing more energy than it took. If we go the opposite direction and this takes more energy than this gives off, then the overall delta H is going to be positive. This will feel cool to the touch. All right. I do question. Instant coffee is made through freeze drying. First, the coffee is made the traditional way. Coffee is cooled until it becomes a solid. Finally, the pressure is decreased and the ice changes to a gas, leaving behind the freeze-dried granules. Identify the 2 phase changes that take place and classify them as endothermic or exothermic. All right, so 2 phase changes. We are, first of all, going from coffee is made cooled until it becomes a solid. So it's becoming a solid from a liquid. So liquid to solid is what? Freezing. So we're identifying that phase change. And then the ice is going to a gas. So if we go ice to a gas, what is that called? Ice to a gas directly. Sublimation. Very good. Good review for your final here, guys. All right. So if something's freezing, what's happening to the heat? It's exiting, right? So this is going to be exothermic. This is going to increase the heat, so this is going to be endothermic. All right, questions? Is that making sense? All right. So, solution of ammonium nitrate, we dissolve 5.02 grams of ammonium nitrate in water. It is at 22.3 degrees. When we form the solution, the temperature drops to 17.3. So my Q sign, is this going to be endothermic or exothermic? Temperature dropped. In the surroundings, the temperature dropped. So the surroundings, the temperature is going down. That means the system is gaining the heat. So that the heat is going from the surroundings into the system. Endothermic, right. So if it is endothermic, then my Q sign is going to be positive. Good? This takes a little getting used to. That's why I like to introduce it now so that we can hit it harder when you get into AP. Okay? All right. Any questions on that? Make sense? All right. So you are going to do your quiz. And you need you'll need a calculator for it. And then you will need this. Probably don't need it by now, but I'll give it to you anyway. And then after you're done, you can either work on quiz corrections retakes, or you can go back and finish your lab up. If you're finishing your lab up back there, then I'll make sure you're wearing goggles. Anybody here still need to finish their lab in the back? One. Anybody here need to finish their lab in the back? Anybody here need to finish their lab in the back? No? Just wanted to see how many setups I need to keep. So if you get done today, let me know so I know that we can clear stuff in the back. Okay? I don't know if you guys will need these formula sheets. No, these aren't the right formula sheets. Hold on. Just one second, I'll do it for you. This is the M1V1 equals M2V2. Do you need the M1V1 equals M2V2? You got that in your head? You need a formula. Anybody need a formula sheet for that one? Okay. You'll need it. You'll need that one. If you need it and you flake during this quiz, let me know and I'll give it to you, okay?